Mongolia, 1971. A Soviet Mongolian expedition excavating in the Gobi Desert uncovered two animals locked in combat. A Protoceratops had its beak clamped around the right arm of a velociraptor. The velociraptor had its enlarged killing claw buried between the neck vertebrae of the Protoceratops. Neither animal had won. A sandstorm had buried them alive, mid-fight, 74 million years ago. And for 74 million years they had remained exactly as they were. Two animals in the last second of both their lives, frozen in the rock, waiting. The fossil is called the Fighting Dinosaurs. It is the most famous specimen in the Mongolian Museum of Natural History in Ulaanbaatar. You can book a ticket and go and look at it. The Fighting Dinosaurs is the most famous case, but it is not the worst. The Cretaceous Gobi Desert was not a stable landscape. The dunes were vast, and the sandstorms that crossed them were capable of burying large animals in minutes. The fossil record from the Jadokta Formation shows multiple specimens preserved in postures that have no explanation except rapid burial. Animals that did not have time to decompose, to be scattered by scavengers, or to sink into sediment. They were buried fast, whole, and alive. Protoceratops specimens are found repeatedly in this formation in postures that suggest suffocation. Bodies intact, limbs folded inward, heads tilted, necks extended. No evidence of predation, no scattering of bones. The animal died with its skeleton still articulated, still in the shape it had when it was alive, because the sand had compacted around it before it could move. The sandstorm that killed the Fighting Dinosaurs froze the moment of combat so precisely that the force the Protoceratops was applying to the velociraptor's arm can be calculated from the compression marks on the bone. It was applying enough pressure to fracture the radius. The velociraptor, in the same moment, had its sickle claw inserted between cervical vertebrae at an angle consistent with an attempt to sever the spinal cord. Neither animal had yet finished what it started when the sand came. Almost every well-preserved theropod dinosaur skeleton in the fossil record is found in the same position. The neck arched backward, the tail curved upward, the limbs drawn in, the spine curved into a tight dorsal bow. It looks like agony. The posture is called Opisthotonus, a word from medicine, not paleontology. It describes a spasm of the back and neck muscles so severe that the head is pulled backward toward the spine. In modern animals, it occurs in the final stages of neurological failure. Tetanus, strychnine poisoning, drowning, severe head trauma. The muscles go into rigid contraction and hold. The animal cannot move. It is conscious, in some cases for an extended period, before it dies. The Opisthotonus posture in dinosaur fossils was debated for decades. Some researchers argued it was post-mortem, that the ligaments dried out and contracted after death, pulling the bones into this position as the carcass desiccated. Others noted that the posture was too consistent, too specific, too identical across species from different continents and different geological periods to be purely mechanical. The current consensus in the literature supports neurological spasm as the cause in most cases. These animals were dying from something that attacked the nervous system. Oxygen deprivation from drowning, toxic gas from volcanic activity, or trauma to the brain or spinal cord. And the last thing the fossil records is the spasm that held the body in the moment of that death. The Kelophysis quarry at Ghost Ranch, New Mexico, contains hundreds of individuals in this posture. All of them, every single preserved animal, died with their necks arched backward. Something killed them all at once, possibly a drought, possibly a toxic algae bloom in the water, and what was left was a mass grave of bodies frozen in the same final contraction. Tar seeps are death traps that have been operating for millions of years. La Brea is the most famous, but it is not unique. Natural asphalt deposits exist across every continent, and several contain fossil records of multiple species dying in the same location across hundreds of thousands of years. The trap works the same way every time. The asphalt is covered by a thin layer of water or dust that conceals its consistency. An animal steps into the edge seeking water. The surface that should hold its weight doesn't. The harder it struggles, the deeper it goes. The asphalt is viscous. It doesn't swallow things quickly. It holds them in place while they exhaust themselves. The struggle can last hours. In some fossil seep deposits, the same species appears repeatedly at different stratigraphic depths, meaning multiple individuals of the same type walked into the same location, across centuries, drawn by the same cues that had killed every animal before them. The bones of the previous victims were covered. The seep looked the same as it always had. And the next animal walked in. Sauropod specimens have been recovered from ancient asphalt deposits in China and South America, showing progressive burial. The forelimbs and ribcage at a different depth than the hind limbs, consistent with an animal that sank front first, struggling with the back legs for an extended period. The bone preservation is excellent. The angle of death is explicit. Not all the evidence is about the deaths that killed. Some of the most disturbing evidence in the dinosaur fossil record is the evidence of what animals survived. A Tyrannosaurus rex skull in the collection of the Black Hills Institute of Geological Research has a circular wound on the left side of the cranium. It is 12 centimeters in diameter. The edges of the wound are rounded, with evidence of bone remodeling. New bone growth filling in from the margins, in a pattern consistent with a healing response that continued for months or years. The wound matches the bite radius of another Tyrannosaurus rex. A T-Rex bit this animal in the head. The bite went through the temporal bone and into the cranium. The animal survived. The bone healed around it. The animal then lived, possibly for years, with a healed bite wound from another member of its own species pressed into its skull, visible in the bone, readable 68 million years later. Face biting is documented across multiple Tyrannosaurus specimens. The face contains fewer scales than the body, the hide is thinner, and the snout is sensitive, full of nerve endings that T-Rex used for fine manipulation. An attack to the face was an attack on the most vulnerable and most sensitive part of the animal. The healed specimens suggest these attacks were not instantly fatal. Some animals walked away from them. Some animals walked away missing significant portions of their skull. Almost every ankylosaur ever found is upside down. This is not coincidence. The anatomy of ankylosaurs, heavily armored dorsal surface, relatively unarmored belly, made them extremely stable on their feet but extremely vulnerable once inverted. If an ankylosaur ended up on its back, it could not right itself. The limbs could not reach the ground at the right angle. The weight of the armored shell pressed down, and the animal could not generate the leverage to turn. The reason so many are found inverted comes from what happens to a large carcass in water. As organic matter decomposes, gas builds inside the body cavity and causes bloating. A bloated carcass becomes buoyant and, in water, naturally rolls. The dorsal side, the heavy armored side, rotates downward. The belly faces up, which means the animals found belly up drowned or died near water, floated, rolled, and sank upside down. But at least 3 ankylosaur specimens show evidence of predation on the belly. Bite marks and scoring consistent with theropod teeth on the ventral surface. This means a predator found the carcass while it was still floating, inverted, belly exposed, and fed on it before it sank. The belly armor that the living animal had protected so carefully for its entire life was exactly what the predator accessed in death. The fossil record is not a record of death, it is a record of specific moments. The sandstorm that hit at exactly the wrong second, the seep that looked like water, the spasm that lasted long enough for the posture to set. Most animals that have ever lived left no record at all. What survives is what was preserved fast enough, buried deep enough, mineralized completely enough. What survives is the worst of it. The fighting animals, the animals that drowned, the animals that sank into asphalt over the course of a long afternoon, the animals that survived a bite to the skull and lived years with the evidence pressed into their bone. The rock does not record the peaceful deaths. It records the ones that happened fast enough, violently enough, in exactly the right conditions. What you see in a museum is the worst day in each of those animals' lives, preserved in precise detail for you. The Western Interior Seaway, the shallow inland sea that bisected North America during the Cretaceous, left behind one of the most complete predation records of any ecosystem in the fossil record. The bodies that sank into its sediment were preserved with a regularity and completeness that land-based deposits cannot match. And many of those bodies show evidence of what killed them. Hadrosaurs, the duck-billed dinosaurs that were the dominant large herbivores of North America, are repeatedly found in fluvial deposits, riverbeds, floodplains, sediment layers consistent with animals that drowned and were carried downstream. The body posture in many specimens is consistent with the bloat and float pattern. The carcass expands with decomposition gas, the belly faces upward, and the body drifts until it either sinks or beaches. Multiple hadrosaur specimens show bite marks and scoring on the ventral surface, the exposed belly, consistent with crocodilians, fish, and sharks feeding on the carcass as it drifted. One specimen from the Niobrara Formation of Kansas, designated FHS-MVP2183, is a hadrosaur that sank into the seaway and was fed upon by at least 4 different species before it reached the bottom. The bite marks on the bones record a sequence. The softer tissues were accessed first by smaller scavengers. The harder bone-associated tissues were processed later by larger animals with more powerful jaws. The sequence is readable in the bone. You can reconstruct the order of events from the marks on a skeleton that has been underwater for 75 million years. The animal drowned. Then it fed half the ecosystem on the way to the bottom. Paleontologists working on predation and death evidence in the fossil record are doing something that has no modern equivalent. There is no field of forensic science that deals with evidence that is 70 million years old. The techniques have been developed specifically for this purpose: 3-dimensional scanning of bone surfaces, energy dispersive X-ray spectroscopy to identify chemical signatures left by biological processes, synchrotron imaging to see internal bone structure without cutting. The field is young. The results keep revising what was previously assumed. A 2016 study of theropod coprolites, fossilized droppings, from the Hell Creek Formation found bone fragments from juvenile hadrosaurs, indicating that adult large theropods were actively preying on juvenile herbivores, not just scavenging adults. A 2020 study of sauropod tail vertebrae from Argentina found a healed bite wound consistent with a large theropod that had attempted a tail strike grab, a predation strategy nobody had proposed for large South American theropods before the evidence showed it had occurred. Every year, the fossil record adds new cases of specific events, specific deaths, specific attacks, specific survivals. The museum is full of the worst days of 150 million years. You just need to know how to read them.